All right. We've been talking about linear regression. And there's a pen. So we've been talking about linear regression, and the idea with linear regression is you have some data and you're going to fit the model to the data, which means when we say fit a model, a couple things have to happen. You first have to propose what that model is. So you have some y hat, some predicted value of responses. It is a function of some of your factors, some of your xi's. So you propose a model, and then you have to develop the coefficients in that model. So how we develop the coefficients in the model is the process that we've been using is we start with what's the sum of the squared error, and then we think about, oh, how do I minimize the sum of the squared errors, and that will give me the coefficients. So from this procedure, we get the coefficients in our model. So I don't want you to get hung up or memorize these particular summation equations, because we're going to do something a little bit differently, something cleaner, and something that's more generally applicable. In this class, what I want you to think about is just the procedure we went through. We just defined these are the sum of errors. When we minimize, we took the derivative or the partial derivative with respect to the coefficients, set them equal to 0, solve the systems of, in this case, 2 equations, 2 unknowns, and then we got equations for those coefficients, and we could get the coefficients in our model. So, does everyone remember that over the weekend? Somewhat. There's some honest, I'm not sure expressions on people's faces. That's okay. So we proposed an initial model which was just y equals bx, where the intercept was forced to 0, and we got a slope of 0.5. Then we proposed the second model where we included a coefficient, a y-intercept, and we got a new model. So the slope, the last thing that we talked about on Friday was, hey, look, the slope changed when we had a different model. And if we think about it, it shouldn't be too surprising. They are different models after all. Okay, then the question we have is the slope significant? Is the intercept significant? And so what do we mean by that is we have this model, y equals mx plus b. So y equals bx plus a. And we have values for a and b. Those little hats remind us that they're estimates of the true values. So we have these estimates, and one thing that we might ask ourselves is we have this intercept, negative 16.92, and we just developed a model previously that had that as 0. Is this 16.92 real or not? Is it significant or not? So we could do the hypothesis test. We could say A, so the mean of that coefficient is 0. The true mean of that coefficient is not 0. And then we'll calculate some statistic, which will be, there's the coefficient, and then we need to figure out the noise in that thing. Formally, I could write a minus 0 over s of a. So, and we get a t-statistic. Is it further out in the tails? Do a two-sided hypothesis test. All that stuff we can repeat for this. And the only thing we need to do that is the noise in the coefficient. So what I've done here, that's this next step. So what I've done here is just thrown down, hey, there's the noise in the slope. Well, I think a little later I've got the noise in the coefficient right there, but we can do this statistic or hypothesis test for A. We can repeat it for B, in which case we need the noise of B. So there's the t-value for the coefficient B. And again, don't memorize either of these formulas at all. Just get the idea of the process we're going through. So a t-statistic, so that we can do the hypothesis test, we need the noise in that coefficient, which is why we started off saying those t statistics. It's always the thing I'm trying to get a handle on divided by the noise of that thing. And we've talked about means, difference between two means. Now we're talking about different coefficients, and they have different values of noise. Okay, this one I'm just throwing down for you, but there is a general trend. It's always built from the individual measurements. So that's S, the noise in the individual measurements. And the one thing that we might want to notice here is xi minus x bar. These are our factors where we took data. And this is saying, okay, if that's my slope, the noise in my slope is going to decrease when this denominator is big, right? So what's going to make this big? If my data, my x's are pretty spread out, right? So you've got x bar here. If my xi's are spread out largely, then this is going to, the more I spread out xi, the bigger this thing is going to be. And I think practically speaking, it should make sense if we've got xi and y, and you took 3 data points there, and we're going to fit a slope through those 3 data points, you'd probably trust the green data points more than the red ones. Does that make sense? Because the green ones are more spread out. We're going to have a better handle on the slope because of it. All right. So now, how do we get the noise in the individual measurements through linear regression? So here it is, but let's think about it a little bit more. We've done this through the whole class. We've talked about this is the way we have been calculating variance. The standard deviation is the square root of that. And that was the formula you've been using since before you got in the class. But in general, if we generalize this variance, it's that we're taking yi minus our best guess of that thing. So we add them up, square them, and then divide by degrees of freedom. So that's add them up. So we take each data point, we subtract our best guess of what that data point ought to be, add all those things up, square that, that's the sum of the squared errors, divide by degrees of freedom. And in this case, well, let's go back one. Back when we said if you know the population mean, that's your best estimate of it, right? And you don't burn up a degree of freedom for calculating y bar, so you have n degrees of freedom, with n being the number of data points. And we did that a couple times when we assumed the blocking interactions were 0, when we assumed the unassigned effects were 0. We've done this formula a couple times. This one here is the one we've done most, and it's saying, well, we generally don't know mu, so we estimate mu with y bar. When we do that, we burn up a degree of freedom, so we divide by n minus 1. Does that all sound familiar? All right, so now we're going to develop this a little bit further, but again, it's the same general concept is, okay, so let's think about this. So we got some data. And we're trying to find the noise in these data. So this right here would say calculate y bar, and you take each data point minus this mean, square it, add it up, divide by n minus 1, and there you've got the noise, right? So you could do that calculation right here. But if you look at these data, you would probably say, that doesn't seem like the right calculation to do. Does everyone agree with that? Because your eye is seeing there is a trend in the data as well, right? There's this linear trend of y increasing with x. So if I calculate it this way, then I'm inflating my noise. Why am I inflating the noise? You could generalize and say you've got the wrong model. So this we're going to start thinking of it this as this is a model. Our model is x is not doing anything with y, therefore we can lump them all together in an average. Right? That model is saying y is constant as we change x. And that's what we've been doing before. We've been just saying it differently. We've been saying, be careful when you average numbers together, make sure you're measuring the same thing. Another way to sort of say that would be make sure that when you're averaging these data points together, they're not changing with, say, some factor x. So that is one particular model. So this is just a degenerate case of this more general variance that we're learning now. So the more general, so this guy right here would be, all right, what if we proposed a linear model there? That's probably what you'd say is the noise would be the data points that are scattered around this model. So this model then, that shows the trend, and these data points are kind of like not really nice points. So we've got some trend there, and the true noise in the experiment is represented by the difference between the data points and the trend that's there, right? So that would be at each data point, we're taking, say, this value, that's a yi, and this value, which is some predicted value right there, and that difference is in the numerator. Then we're going to square them, add them all up, and now the degrees of freedom, it's very similar to this case. We have to ask ourselves, well, how many degrees of freedom did I burn up by getting this y hat? And it depends on our model. So before, when it was the average, we just burned up 1 degree of freedom because our model had one coefficient, if you will, just the mean. But here, the c is the number of coefficients in the model. So when we have our model y hat equals a plus bx, the number of coefficients is 2, a and b. So we have to burn up 2 degrees of freedom to calculate those things, and we have to account for that when we're calculating the noise. All right. Does that make sense? And in shorthand, we're going to be writing it this way a bit. So SSE, sum of the squared errors, that's the summation part. N minus C, we could just say in general, variance is going to be the sum of the squared errors divided by the degrees of freedom. And so one thing we have to be careful about then is the fact that it is model dependent. And maybe do that. So if we proposed a model like this, like that purple one, and we try to calculate s squared, or we could, right? We're going to get a huge SSE here, right? So if we calculate the noise from the purple model, it's going to be much bigger than the noise of the individual measurements from the linear model. So keep in mind, this value now, it depends on the model we pick. So we have to pick the right model to get the right level of noise. If we've got the wrong model, this is going to be inflated. Probably. There's another way we could get the wrong model. But in this situation, that purple model will give us a large estimate of the individual measurements. Does that make sense? All right. So when we think about getting into Excel and calculating this, how do we do this? Here's the brittle hardness example. We had hardness, tensile strength, and we proposed this model right here. We got the coefficients from before. A was 0.54, B, or minus 16.92, B was 0.54 something, right? So you could type that into Excel and say, all right, put 500 in for X, and I have A and I have B. I can calculate a predicted value that I predict when the hardness is 500, the tensile strength will be 254 or something. Does that make sense? Does everyone see how we get this number right here? So we type into Excel, well, you don't type in the y hat to Excel, but you say minus 16.92 plus whatever that was times X. You put in 500 for X, and you get that value there. And then you copy it down, and there you get your model predictions. The errors are, there's my data, there's my model, that's my error, the difference between those two. Square each of them and add them up. That's the sum of the squared errors. Does everyone see that? This is just the other parts of that formula that we've used before for A and B. But to get S squared, we take SSE and we divide by degrees of freedom. So what's the number there in this case? Anyone got a number? Heard of 3. How many data points? 5. How many coefficients in our model? 2. So we have A and B. So yes, we're divided by 3 in that case. So that gets us S squared. Take the square root. There's S. That's our estimate of the noise in individual measurements, and it is based on how these data points are sprinkled about our model. If we've got the right model, then we've got the right level of noise. All right, then this is just saying we can put the A coefficient on trial as well. If to get SA, there's the number of, there's this S from before, and we can calculate, these values are just, these are just numbers. Can't stress that enough. Those are numbers that we get off our spreadsheet. We get a value there. They're pretty straightforward, I think, how you get those in Excel. And you can do those statistical tests. You can do confidence intervals or hypothesis tests. Excel will give you both of those values. Okay. Now, how do we read this stuff on Excel? So nobody's really done much of a linear regression on Excel, right? Okay. Let's see if I've added in the analysis tool pack in this one. If not, I'll do that later. So while that's going, hopefully, this is the output of a regression analysis in Excel. So just looking at what you get from it. So let's start right here. So intercept, that's your coefficient, right? So that's A. X variable 1 is B. You can sometimes highlight the labels to get a little bit more descriptive values here, but that's a detail. So A, the intercept, remember that was that 16.9, and B, the slope was this. So this was for that model. And Excel says, here, your model is minus 16.9 plus 0.54 times x. And it was that same brittle hardness value data that we had before. And this tells you there's n, there's s. We'll talk about r squared in a little bit. The ANOVA table, that's where we get n minus c. You can come up with that there. And there's so s squared shows up in that's a mean square of residuals. Remember, residual was another name for errors. And this is the sum of square. This is sum of squares. So if you take sum of, so that's SSE, that's n minus c. You divide those two, you get s squared. In ANOVA speak, it's called the mean squared. ANOVA is just analysis of variances. We haven't talked about it, so the s squared you can get there, or you can get s from up there. It's a bit redundant information, but that's fine. Then, where the rest of this comes, these are these equations which we're not going to do much with, frankly, but that's where you get the coefficients, and then the standard errors are, that's the standard deviation of B, that's the standard deviation of A. The t statistic is just dividing this by this to give you the t, just like in a hypothesis test. And there's the p-value associated with that t. It is two-sided. It's a two-sided test. And then it gives you the confidence interval on each of those. And for some reason, it gives you this confidence interval, then it gives you another confidence interval exactly the same afterwards. There's got to be some option in there why it gives you two confidence intervals. I haven't found it yet in Excel, though. But from these data, we can interpret them. So what do you think? The slope, is the slope significant? If you're doing a hypothesis test on the slope, do you think it's significant? Who says yes? Who says no? Okay, slope is this guy. P-value is very, very, very small. Does that mean it's significant? Yes. Confidence interval, another way you could look, does the confidence interval include 0? It doesn't include 0. Both those things are saying, yes, that slope is significant. What about the constant, the intercept? Sometimes you'll see this called the constant, depending on the version of Excel or Minitab that we're using. It's the same thing, though. What do you think about that? A, is it significant? P-value of 0.2. What's usually our cutoff for p-value? 0.05. It's much bigger than that. What does that mean? Insignificant. Confidence interval does include 0, so we would say that intercept is insignificant. All right, so let me see if I've got this in here. They moved it on me when I thought it was in this what if analysis. Solver's not the same as regression. I'll have to go back and add this. Every version of Excel hides. It used to be here, it used to be in a different menu entirely, but I'll have to go back before I do an example. Minitab does give you the same output. So it gives you the same information on output. So you can do, you think, I could probably do this on Minitab, you'd be right. and it tells you the same sorts of stuff. And so I'm not going to go over this. You can read the, this corresponds to this. This is explained here. So it tells you where all the same information is. The additional information that Minitab gives you is unusual observations. So that means I may or may not have an outlier. It's just alerting you. It's not telling you you have an outlier. It's saying you might want to look at this. This residual has this. This is like a t-value for the residual, and it's saying this particular residual is about 2 standard deviations away from the mean of all the residuals. You might want to look at it. It seems like it could be an outlier. Yeah. In Minitab, there's a regression tool in Minitab. I think you can use it in the toolbar or the menu Then, one thing we haven't talked about, you can predict a new value. If you have a model, you can say, use my model to predict a value at a certain observation. So you can put in an X and say, give me a prediction. We'll talk about that when we get into the response surface methods, because once you have a nice model, what you probably want to do is use it to predict, here's the optimum settings for the X's, and then this is the Y that I would predict from it. And we'll talk about the difference between a prediction interval and a confidence interval soon here. The last thing that we want to do, so we've done a couple of the goals. We've kind of gone through this and said, first thing is we want to propose a model, and then we want to fit the model to the data, which means get the coefficients in the model. Then we want to test each of the coefficients for significance and trim our model down so it only has significant terms with a couple of our caveats there. And then once we have that parsimonious model, then we want to use it, which means we want to use it to make predictions. So we're going to take and say, well, I think the optimum values of my factors are this, this, and this. You throw them in your model, and you are going to get some number out of your model. What you want to do, or what you should be doing, is saying, based on my noise, I get some number there, plus or minus some other number. Right? And that'll be a confidence interval on that model prediction. So just like previously, we need the confidence interval is t times s of y hat. So s of y hat, again, it's given to you here. We'll develop it, the one we want, but that's the noise in a model prediction. So again, that general concept of what's the thing you're trying to say something about, you got to match the noise to that thing. It's a model prediction, so we need the noise in the model prediction. And then out in front, we need a t-value, and for some strange reason, just how statistics grew up is you can do that, and that would be consistent with whatever we've done, but how people have just done it over time is to say, well, we know that t-value is between 2 and 3. For model predictions, just a convention is just make it easy and say, report your model predictions, with the plus or minus 2 s of y hat. So you just pick a 2 for your t-value. A bit unsatisfying, but it is simpler. So anyway, don't get too worked up about that. It is just a convention that people use. So therefore, we have to be able to handle that. If that's what they're going to interpret your results are, it's sometimes very often it's better to show the results that way, even though you would have a more precise value by actually calculating a t. So then to finish off our example here, we pick some x values. So various hardness values here. we calculate a y hat from our model. We may have had a plus bx as before. Then we use that formula above. We'll use a different formula later, which does reduce to the same thing. We get the noise, and then we can calculate the two confidence intervals. So that's what it would look like there. You can maybe see some trend in there is those dotted lines seem to be closer together here than they are there. Does everyone buy that? Does that look obvious? That's a little strange, maybe. So when we look at this, that x naught is the location. It's saying if you're going to predict a value at x equals 300, that's what you put in there. And that means that business right there is the closer you're predicting to the mean, the smaller this part is, right? What if you're predicting right at the mean? That whole term goes away. And S of y equals S, if you're predicting at x naught equals the mean, that's our noise. Does that look familiar? Okay, everything comes together, and it is as it should be, right? That's like the central limit theorem when we're doing stuff with the mean. So, okay, that's good. And then it also is telling us the more general situation of the closer we are to the mean, the better we know, the better our model will predict. And that also, I guess, intuitively kind of makes sense. We've got data all the way around here. If you're going to predict right there, you're right in the middle of your data. So that's probably a more sure thing than if you're predicting way out here. In fact, here you're actually extrapolating beyond your data point, but over here you just have one data point on this side, and this data point, you know, may not be saying a whole lot about this data. All right, so. Okay, so that gives you the whole overview of what we're doing. Again, propose a model, get the coefficients, test the coefficients, simplify your model to a parsimonious model, and then use it to make predictions. And so that's a very powerful thing, right? So now we figured out how to design experiments to get a model, and now we're going to use that model appropriately so we can say, you know, here is our data tells us that this is what we're going to get, and here's a confidence interval in it. But I've only showed you the example of the very simple model, y equals b times x, or a plus bx. And we know that we've been doing full factorial stuff and other designs where we have multiple factors. We don't just have one x. We don't just have temperature. We might have temperature and pressure and their interaction. How do we expand this linear regression analysis to include those? So this is more of a model that we would be looking at. We have an intercept, or this was the mean, remember, and we could develop these models from full factorial. Coefficients were f(x) divided by 2. We may have effective x1, x2, and so forth. So that is what's the form of the linear models we're going to be looking at, and then that's an example of not just a full factorial. So this would be some response surface method model with k equals 2. We have main effects, we have the quadratic terms, and we have the interaction term. So that is a linear model, and we can use linear regression to fit the model to the data, which means it will give us those coefficients. Next step would be, let's test these coefficients with hypothesis tests, see which ones are significant or not, and reduce our model down to the parsimonious model, and then use it. And I wrote this in case you had some experience in Excel. If you don't, you guys haven't done much linear regression in Excel, so I won't mention this too much. So that's what we need to do. So we need to go from a plus bx to getting these models where we have x1, x2, x1, x2, and those kind of things. So to do that, we're going to get everyone's kind of favorite memories from, I don't know, when did you guys use matrices the most? Was it statics? Pardon? Everywhere. Now they're everywhere. You can't get rid of them. You can't run from them. Okay. So it gets so complicated with that algebra that we did was already messy for two coefficients. If you can think of, if we've got 8 terms in our model and you're going to solve 8 equations, 8 unknowns simultaneously, you instinctively know we better be using some sort of matrix method of doing that in order to do it reasonably. So the first thing that we have to do is define our terms. So we have y. Those are the results. So that's the results of our data. If we think about our full factorial design, experiment 1, we got a response of y equals that. Experiment 2, we got that. On down to the nth experiment we took data, and we got that number there. Is everyone okay with that? Okay. B, those are the coefficients in our model. So that's the mean, or the constant. There's the x1 coefficient. There's the coefficient in front of x7, whatever that is, if n is equal to 7. Or if our model has 7 terms, I should say. This y hat vector is your model predictions. And finally, that is the full computation table. So again, we're trying to think of this like a full factorial design. The computation table is, right, that was that mean column. That was, say, x1 and x2 and so forth, and this would be some higher order interaction down here. So if you think about your Excel where you have the full computation table, you highlight that whole thing, and that's your X matrix. That's the experiments that you did. Let's see if I've got covered up here. So, everyone okay with defining those? Are there any questions of what each of those things are? All right. So now the method we use to fit the model to the data, that's what we mean by fitting the model. We need to find B naught, B1, B2, B3, all those things. Same method. We need to find our SSE and to minimize that. That's going to give us that B vector. So we need to just do this all in the matrix world. And so the first thing is the sum of the square root of errors, right? That E is errors, is just like we had before. It's our data minus our model predictions. So that means I'm going to take y1 minus y hat. I'm going to take y2 minus y2 hat and add them all up. Does everyone get that? That's what this is doing right here. That's the errors. So now what we need to do is we need to take that minus that and square it, that minus that and square it. So We have our error squared. We have our, so let's say we have an error here. And you have some vector there with those errors. y1 minus y1 hat, y2 minus y1 hat. And I want to square this guy. So if I'm going to do that in the vector world, I have to take that thing and multiply it. I've got to transpose it and then multiply it together, right? So, or put the transpose up there. So that's what this is saying is, okay, I'm going to transpose the error and multiply it together. So we just have to just be careful. We're going to do the exact same thing, but we have to just say, all right, well, that dimensionality of the matrices, we have to be careful with that in the order we do it and how we do it. So that is just squaring, if you will, the errors and adding them up. Okay. So that's the same thing as that. We're just keeping track. Yeah, it's a vector. It's got dimensionality. We need to be aware of that. So now, we're going to do the same thing we did before. The next step was always, well, what model are we using? What y hat? And let's put it in there. So our model is always x times b. So x, all the experiments we did, b was all those coefficients, and that gives us our model. Or b is all, let me see, there we go. So we put that in there, and then we multiply it through, and there's just details that you probably haven't gone over too much. Anyone do linear algebra in taking linear algebra class at all? Okay, so we're not going to get too hung up on the details. When you multiply those things together, you get things, and you say, okay, that makes sense. I've got y, and I got a transpose in a y. I got 2xby. You just got to be careful of, okay, I got to pre-multiply this or post-multiply that to make it work out with the dimensionality, and then you multiply the last two terms, and you get that. So we've got that, and now, just like before, we took the derivative with respect to the coefficients and set it equal to 0. So the coefficients, that's the b. So we're going to take the derivative of this guy with respect to b and set it equal to 0, and it behaves just like you would hope. So this term here, there's no b, it goes out. This term, you've got b to the first. Take the derivative, it does that. Here you've got a b squared, so you have 2, whatever's left, and b minus 1, b to the first. So you get that term. That probably is what you'd expect. If you had to guess on what that derivative was, you'd probably guess something like that. Something close to that. So we take the derivative of SSE and set it equal to 0. So to do that, we've got just rearranging this now, getting rid of the 2's, bringing this over that side. We've got that. And our whole point for doing this was solving for the coefficients. And remember, we can't, if all these are vectors and matrices, you can't divide by a matrix, right? You have to multiply by its inverse. Everyone remember that? Okay, so we have to take this guy and pre-multiply both sides by the inverse of that guy, which is right there. And that will give us our coefficients in our model. So it's also very, very fun. I always say this, there's also different ways where this makes you feel like a cool person when you talk to other people. If you say things like x transpose x inverse times x transpose y, it sounds like you've said something. And indeed you have. You've said the most important equation that you probably use in handling data, which is this linear regression. So if you know, I did these experiments, I got this data, I'm going to propose a model which gives me the form of B, and then I'm going to do the matrix math and fit the equation or the model to the data. So that's an equation. That's the one we're going to be using. We're not going to be using those summation ones. We're going to be using this one right here. And indeed, they end up being the same thing. So let's take a look at this right here and see if we can prove that these are one of the same. So what we're going to do in this problem is let's just take one step back and say, let's compare this equation. So this is the algebra-based stuff that we did in the first two examples. Right? So we called this one A before. I'll just call it B naught here. So what I'm asking you to do here is say, I'll call this the algebra way. The algebra way gave us this. So you can go back to the algebra and see how we get this. But let's see, can we get that answer by doing the matrix method? So the first thing that we have to do is we have to define X, we have to define B, we have to define Y. Right? So these are vectors, matrices. So I would say first thing probably to start with would be let's define B, then Y, and then leave X till the end. So start going through that. See if you can pull those together. It's a bit of a stretch. Don't feel bad if you are a bit lost right now. It should come together when we do quite a few more examples. Looks like people are having trouble getting going. Let's tweak this a bit to make it a little bit more accessible. Why don't we go back to the brittle hardness data? Essentially do the same thing. And let's use this, or even better, this. Let's get the coefficients for the brittle hardness. So we've got X transpose X, inverse X transpose Y. The brittle hardness data had X and Y. So X was 500, 431, 70, 285. that was the data. So I think that'll be a little bit easier than doing a bit too much symbolically. So that's the data. Can you define x, y, and b for the for this model? And let's try to fit that to the data. All right, that'll have to be it for today, though. We'll pick that up tomorrow.